You type a few words into a search box. And behind that box sits a haystack of billions of web pages, almost the entire written output of humanity, jumbled together with no order at all. In about half a second, Google reaches into that haystack and hands you, right near the top, the handful of pages actually worth reading. Which raises a genuinely strange question. Out of billions of pages, how could a machine possibly know which ones are important? The answer that built Google is almost a riddle. A page is important if important pages link to it. Read that again, and it sounds hopelessly circular. You'd need to already know what's important to figure out what's important. And yet, somehow, it works perfectly. The trick is to stop fighting the circle and start letting it spin. Start with the obvious idea. Every link pointing to a page is a little like a vote of confidence. Somebody thought it was worth pointing at. So just count the votes. Add up all the incoming links to each page, and whoever has the most wins. The page with the most links to it floats to the top of your results. Simple, tidy, and pleasingly democratic. And for a little while, back in the early days of the web, search really did work roughly like this. One link, one vote. There's just one fatal problem. Counting links is almost insultingly easy to cheat. Want to promote a page? Spin up 1,000 worthless junk pages of your own, empty, automatic, meaningless. Then point every one of them at the page you're boosting. Suddenly it has 1,000 glowing votes, and not one of them means a thing. Its importance is completely manufactured, a tower of fake endorsements built in an afternoon. And there's a deeper rot underneath. In a pure count, a link from a random nobody page counts exactly as much as a link from the New York Times. If every vote is equal, no vote means much. That weakness, that links could be faked, didn't just create a few cheaters. It spawned an entire global industry dedicated to gaming the ranking, search engine optimization. At its worst, that meant link farms, vast networks of thousands of empty, automatically generated pages, built for no reason except to link to each other and pump up someone's score. So Google has spent its entire existence fighting back, constantly rewriting its algorithm to sniff out the fakes and punish the manipulators. It's a permanent cat-and-mouse war. The moment one loophole closes, someone finds the next. The reason search even stays useful is that this fight never, ever stops. So in 1998, two Stanford graduate students, Larry Page and Sergey Brin, added a single twist that changed everything. A link shouldn't just count. It should count more when it comes from a page that is itself important. Votes get weighted by the voter. One link from the New York Times should outweigh 1,000 links from anonymous junk. Endorsements from the trusted matter. Endorsements from nobodies barely register. Importance, in other words, flows through the links. A page hands a share of its own standing to everything it points at. But look closely at that idea, and you walk straight into a paradox. To know how important this page is, you first need to know how important the pages linking to it are. Their importance determines its importance. But to know how important they are, you need to know how important the pages linking to them are. And so on, with no bottom in sight. The definition chases its own tail, forever. It seems like you can't even get started. There's nothing solid to stand on. At first the scores slosh around wildly. A page surges, then sags, then surges again. But with each pass, they settle a little more and a little more. Start by being naive. Give every single page the exact same small score, perfectly equal, no page special. A blank slate. Then run one simple rule, over and over. Every page takes its current score and passes it along its outgoing links, split evenly among all of them. At first the scores slosh around wildly. A page surges, then sags, then surges again. But with each pass, they settle a little more and a little more. Until, remarkably, they stop changing at all. The circular definition quietly converges onto one single, stable set of numbers, and there's your ranking. Here's the most intuitive way to picture what those final numbers actually mean. Imagine a person surfing the web completely at random. They land on a page, click a random link, land somewhere new, click again, on, forever, with no goal and no memory. A page's PageRank is simply the fraction of all that endless time the random surfer spends sitting on it. Popular crossroads of the web get visited constantly, lonely dead ends almost never. Important pages are exactly the ones you keep washing back to, no matter where you started. The score is just, how often do you end up here? And that stable set of scores has a precise name in mathematics. Stack every page's score into one gigantic list, billions of numbers long. Now describe the entire link structure of the web as a single colossal grid of numbers, a matrix with a row and a column for every page that exists. The PageRank scores turn out to be the principal eigenvector of that matrix, the one special direction the whole enormous system settles into and then holds unchanged. The entire web, all of it, distilled down into a single vector. That quiet line of mathematics is, more or less, what you query every time you search. Now, you might reasonably ask, how do you actually find that eigenvector for a matrix with billions of rows? You don't solve it with clever algebra. You do something almost crude. You just take a starting guess, multiply it by the matrix and look at the result. Then multiply that by the matrix. Then again. It's the random surfer's wandering, written as repeated multiplication. Astonishingly, you don't need many rounds. Something like 50 passes over the entire web is usually enough for the numbers to lock into place. Each pass drags the scores closer to the true eigenvector, and the gap shrinks fast. 50 multiplications and billions of pages are ranked. There's one last patch needed to make it truly work. Some pages are dead ends with no links out, and some clusters trap the surfer in tight little loops where importance pulls up and never escapes. So about 15% of the time, the random surfer simply ignores the links altogether and teleports, jumping to a completely random page, anywhere on the web. That small, constant dose of randomness is the famous damping factor. The surfer follows links 85% of the time and rolls the dice the rest. It keeps importance from getting permanently stuck, and it guarantees the whole system settles to exactly one clean, well-defined answer. And it's worth pausing on just how much rode on this one piece of linear algebra. That recursive, circular little idea grew into Google, and Google grew into a company worth, at times, around $2 trillion. Here's a detail most people never hear. Larry Page invented PageRank as a student, so the patent didn't belong to Google. It belonged to Stanford University. Google licensed that patent from Stanford in exchange for shares in the young company, betting the school would rather own a piece of the future than a slip of paper. When Stanford eventually sold those shares, that single licensing deal had turned into roughly $336 million. Not bad for one eigenvector. And the idea turned out to be far, far bigger than web search. The very same math escaped the search engine and spread everywhere. It now ranks the influence of scientific papers by who cites whom, finds the key players in a social network, picks out the most critical proteins in a living cell, and even spots the must-use roads in a city. Because PageRank captured something genuinely deep and a little philosophical. Importance is not a thing a page owns by itself, sitting there in isolation. It's something the entire network decides, together, a single eigenvector, quietly agreed upon by billions of links, all pointing at each other at once.